Okay, yeah, there we go. Okay, right, so I'll just rewrite the title briefly. So tangent spaces to affine Schubert varieties. And counterexamples to the reducedness conjecture. And this is joint work with my collaborators Jiuzhu Hong and Huan Yu. So joint with Jiuzhu and Huan. And okay, so I'm going to start in the following situation. So I'm going to take G to be a simply connected linear algebraic group over C. And I'm going to fix a maximal torus inside a Borel inside G. And this way I can talk about the co-characters and the characters. Sorry. And because I've chosen a maximal, I've chosen a Borel, so I can talk about positive roots. So I have my root system. I'm going to take phi plus. This is going to be the roots in Li B. And then I have a base, so delta plus is going to be a collection of simple roots, alpha 1 through alpha n. And with this, I can talk about dominant co-weights. We've seen these a couple times already. So the dominant co-weights are going to be the lambda, such that the pairing of lambda and the alpha i's is greater than or equal to 0 for all I. Okay, this is some notation that we've all already seen. I'm going to need the affine Grassmannian. So we have the loop group. This is going to send C algebras to G valued in R Laurent series in a uniformizing parameter T. We have the arc group, which sends R to G valued in Taylor series over T. And then we have the affine Grassmannian, which is the quotient. And this is represented by an ind projective in scheme over C. I sympathize with everyone else. Okay, so the idea is that these dominant co-weights are going to parameterize an interesting collection of subvarieties or subschemes of the affine Grassmannian. So for all dominant co-characters, we're going to associate two subschemes. So first is the affine Schubert variety, Gur lambda. And the second is going to be what I'm going to call the Finkelberg-Mirkovic Schubert scheme. So these were introduced by Finkelberg and Mirkovic basically in about 99. And these are often also called the conjectural modular description of affine Schubert varieties. So conjectural modular description. Okay, and what are and these are both projective subschemes of the affine Grassmannian of finite type over C. And they have the following properties. So the first is that the affine Schubert varieties are singular, usually, but they're quite well behaved. So they are normal, they're Gorenstein, they have rational singularities, and in particular what I want to focus on today is that they are reduced, essentially by definition. We define these affine Schubert varieties to be closures of cells with the reduced-induced subscheme structure. by some easy calculation, you can check that the reduced subscheme underlying these Finkelberg-Mirkovic Schubert schemes is the affine Schubert variety. So these Finkelberg-Mirkovic Schubert schemes are possibly non-reduced thickenings of these affine Schubert varieties. And as the name would suggest, the what am I doing wrong? The affine Schubert schemes have a very nice functor of points. So have an easy functor of points, basically given by R lattices, compatible families of R lattices inside finite dimensional representations of G tensored over formal Laurent series over R. I won't write the full definition here for lack of time, but okay. So a long-standing conjecture or question, but basically conjecture of Finkelberg, and I'll call it the reducedness conjecture, is that these are the same. And this is why they would call the conjectural modular description. You want to have a modular description of these affine Schubert varieties. And so equivalently, the conjecture is that these Finkelberg-Mirkovic Schubert schemes are reduced. And there's some recent progress in this direction. So there's a theorem due to Kamnitzer, Muthiah, Weeks, and Yacobi in about 2017, which states that for G equal to SLN plus 1, the affine Schubert schemes are reduced. And our theorem is the following. So first, let G be of type E8. Then the tangent space at the base point of the affine Schubert variety associated to theta check is basically a copy of the adjoint representation. But the tangent space at the identity of the Finkelberg-Mirkovic version for theta check is 2 copies of the adjoint. Similarly, for G of type E7, the tangent space at the base point of the affine Schubert variety associated to omega 6 check is equal to 1 copy of the adjoint. And the tangent space of the Finkelberg-Mirkovic version is 2 copies of the adjoint. And lastly, when G is simply connected of type E6, the tangent space at the identity of the Schubert variety associated to omega 1 check plus omega 6 check is 1 copy of the adjoint, whereas the tangent space at the identity of the Finkelberg-Mirkovic Schubert scheme is 2 copies of the adjoint. And so a corollary is that the reducedness conjecture fails in E8, E7, and E6. So reducedness is false for G of type E8, E7, and E6. So who cares? Who cares? There are a couple groups of people who might care. So the first is that the geometry of these affine Schubert varieties appears in geometric Satake and geometric Langlands more generally. So the Gur lambda bar appear in geo-Satake. But the point is that the structure sheaf of these affine Schubert varieties does not. So if you only care about these things in terms of categories of D-modules or perverse sheaves on them, you don't care, which maybe some of you. But there are two other people who do kind of care about the structure sheaves of these affine Schubert varieties. So one group is this group associated to Kamnitzer, Muthiah, Weeks, Yacobi, Webster, etc. So there are slices inside affine Schubert varieties, lambda. So these are affine Poisson varieties. And the quantizations of functions on these slices are called the truncated shifted Yangians. And this is kind of the motivation for Kamnitzer and his colleagues to understand these, is they wanted to understand these truncated shifted Yangians. These are appearing in geometric representation theory. And these groups of people do have to care about these counterexamples. Basically, there are a bunch of conjectures about generators and relations for these rings of functions on these slices. And these conjectures come from the Finkelberg-Mirkovic description. And what this says in E6, E78 is that those conjectures need to be modified. Those are describing some non-reduced scheme supported on the slice. So this makes the study of Yangians, truncated Yangians, and slices more difficult. And then the third group of people who might care about this stuff are local models people. So the geometry of curve lambda is closely related to the geometry of local models, G lambda, local models for Shimura varieties. And in this context, there's a recent work by Kizin, Papas, and Zhou. And what they do is they, maybe what I can say is they produce a list of lambda in classical type, in types A, B, C, D, such that the tangent space at all mu of the Schubert variety is equal to the tangent space at mu of the Schubert scheme. And they use this to prove things about the geometry of the local models. And what our counterexamples say is that you cannot do this in, for instance, E6. So this affine Schubert scheme for E6 right here will appear if you want to talk about Shimura varieties for E6 and local models of them. And this is telling you that you cannot try to understand this geometry in terms of the Finkelberg-Mirkovic Schubert scheme. So it seems to make life harder for those who care about local models and functions on slices inside affine Schubert varieties. I believe my time is about up.
Thank you for the introduction. So today, as Jared said, I'm going to talk about the Abel-Jacobi map over Scholze's twistor P1. All of this is joint work with Maximilian Haug. So the talk is going to be divided in three quick parts. First, I'm going to talk about the main motivation for this project, which luckily was recalled also yesterday in Minja's lecture. Then I'm going to talk about the context in which we're working, which is Scholze Archimedean geometrization. And then I'm going to talk about our results. So the main motivation comes from this article of Fargues. I have a terrible French, so I'm not going to pronounce the title, in which he proves class field theory using the simple connectedness of the map of the Abel-Jacobi map over div D. In particular, its main point in his article is that letting E for now be a non-Archimedean field, and XA, the Fargues-Fontaine curve relative to a perfectoid ring of A over E, the dth Abel-Jacobi map from the space of divisors of degree D to the space of line bundles of degree D, pick D, sending a divisor D to the associated line bundle, as simply connected fibers for D bigger than 2, meaning that all finite L coverings over them are trivial. So let's recall 1 second Fargues' proof in steps, although in a worse way than Minja did yesterday. So since pi1 of D1 is the Weil group of E, still an Archimedean field, we get that any character of the Weil group is equivalent to a one-dimensional local system on D1. given L, it box tensor it to an entire local system over D copies of D1, and then descend it to an entire local system now on the D-symmetric power of D1. But as Min just said yesterday, the D-symmetric power of D1 is div D. Now pay attention to the red parts. And for D enough, the Abel-Jacobi map is simply connected fibers. So we automatically obtain an entire local system ED on peak D. It then shows that this ED actually comes from entire local system E on peak 1. And peak 1 is just the classifying stack of the multiplicative group of our local field E. And so the character with which we started actually comes from a character of the multiplicative group of the local field, which implies in particular that the Abelianization of the Weil group is the multiplicative group of the local field, and that's local class field theory, as we all know, hopefully. So let's switch context, and okay, maybe this is not familiar to everybody, but don't be afraid, I'm going to say what we need. So the first slogan which you need to remember is that the analog over the real numbers of the Fargues-Fontaine curve is the Simpson twistor, which is the only non-trivial Brouwer-Severi variety over the real numbers. This is the project description. So we will work in the category, we will work over the gaseous complex numbers, and our geometric setup is that of the category of totally disconnected stacks, which are sheaves with respect to the descendable topology over totally disconnected algebras. Now, totally disconnected algebras in one direction are analogous to perfectoid spaces, and in another direction can be seen as some nilpotent thickenings of spaces of continuous functions over some prefinite set S. In particular, to any totally disconnected algebra A, there is an underlying space S associated. Now, the category of totally disconnected stacks is natural functors from the category of topological spaces, complex analytic spaces, and real analytic spaces, which we denote respectively as Betty, SAN, and SLA. So the first main difference is that in this context, the linear algebra is not given by L-adic sheaves, but is given by quasi-coherent sheaves. And also, before I was talking about étale local systems to talk about representations. Here in this context, we are going to talk about vector bundles to talk about representations. In this case, over the classifying stack of Lie group, which is going to be point mod GLA for G Lie group. So now this is the key definition given by Scholze, which is the definition of a family of twistor varying over a totally disconnected algebra A with underlying space S, which can also be seen as the space of the geometric points of A. So Scholze defines the family of twistor as the following push out. On the upper left, we have the analytic spectrum of the continuous functions from S to C. This maps to a specified point of the twistor, which is the infinity point, meaning the point which descends from infinity from the projective line. And what you see on the upper right is just the algebraic base change of the twistor to the space of continuous functions from S to R. The left map you can think of as some nilpotent, some reduction map. And then you take the push out of this diagram where P1A on the lower right is just notation, is not actually just the base change. Then, through this definition, we can make sense of, also in this context, of Banach-Kolmé spaces, the Archimedean Banach-Kolmé spaces. And so, for example, the Banach-Kolmé space given by sending a totally disconnected algebra A to the global section of the structural sheaf of P1A is going to be RLA, analogously to what happens in the Fargues-Scholze context. And in particular, we have the following analogs. So the space of degree D divisors over the twistor P1. We have the classifying stack peak D, which, okay, we have peak D, which is the space of degree D line bundles, and this is just the classifying stack of the multiplicative group of the real numbers. And we know that there is a natural equivalence between semi-simple vector bundles over D1 and representations of the real Weil group, semi-simple representations, which I remind you is just given by this subgroup of the unit quaternions, in case you didn't remember. Now, let me also say that by changing to C, one obtains also a curve with respect to the complex numbers, which will have two thickenings, because the cover from P1 to P1 twistor is a degree 2 cover, well, of course. And, well, this is what I wanted to say about the context in which we are working. So, this is our main theorem. Let E now be an Archimedean local field. Pull back along the map, along the Abel-Jacobi map, induces an equivalence between the two following Picard groupoid. okay, which we write as this mapping anima. Now the classifying stack of the analytic GM plays the role of the classifying stack of GM in this context. And in particular, any line bundle of D1E is pulled back from pick 1E. So this yields real, like Archimedean local class field theory, if this is, like, if you want to think about this as a non-trivial statement. Okay, so let's talk about the strategy of proof. We treat the case where E is equal to C, and we descend the results to the real numbers. And in this case, we look at the dth Abel-Jacobi map, which goes from div D to pick D. Now, this is a presentation of div D and a presentation of pick D. And so we see that the fibers are given by the dth, by the punctured dth Banach-Kolmel space. And this is just A2 analytic times CD minus 1 Betty minus the origin. So now there are two problems if one tries to adapt Fargues' proof. And that the 2 points which I first highlighted in the proof of Fargue fail, meaning 3 and 4 fail. So intuitively, the D symmetric power of D1 is not div D, which is a problem. And the problem comes from lifting the factorizations from after dagger reduction, or from the dagger reduction, yes. Because this acts as like some kind of nilpotence. The dagger reduction is the nilpotent thickening I talked to you about before. And since we are working in the quasi-coherent formalism, we cannot be done by just using simple connectedness of the fiber. We actually need the contractibility. But you may notice that as D gets bigger, this space becomes more and more connected, D plus 1 connected, to be precise. So let's talk now how we fix these problems. So the solution to the first problem is that for these bigger or equal than 2, we can define an open locus of DD, which we call div D, Hodge state smaller or equal than 1 for some reason that you can discover if you open the paper. The complement of this locus, in some sense, has codimension 2. Actually, something that I should remind the audience is that in this context, we don't have a notion of dimension, we don't have a notion of connectiveness, and this is just an intuitive picture we are trying to give. So over this locus, the multiplication map from the dth symmetric power of D1 to div D is actually an isomorphism, and we have the following equivalence of mapping anima, which just says that we can extend line bundles uniquely. And this is well because, again, intuitively this has a complement which is closed of codimension 2. Furthermore, in order to actually obtain contractibility of fibers, we pass to a huge colimit of div Ds. In some sense, these are given by multiplications along the sections corresponding to the thickenings of the curve. And we prove that this colimit is isomorphic to C infinity minus the origin Betty, which is quotient C star LA. So now the fibers are just going to be given by C infinity minus 0 Betty, which is going to be a contractible space. Summing up, since box tensoring gives us a series of compatible maps to all div Ds, we get actually a map to our huge colimit. But now the Picard anima of this huge colimit is naturally isomorphic to that of pick 1. And so box tensoring gives us an inverse to the pull back along the Abel-Jacobi map. So I forgot to keep track of the time, but I think that I'm in time, maybe even a bit too fast. Surely I want to thank you for your attention, and if you have any questions, I'm here.
All right, thank you for giving me the opportunity to speak here. So to set notation, let's let G be a split reductive group over a non-Archimedean local field, E. Now, for the purpose of this talk, I'm going to introduce sort of 3 tiers of complexity for L parameters, which go by different names, but I'll be using David's notation. So generous, sorry, I should semi-simple. So all L parameters in this talk will be semi-simple. So if I forget to mention that, we're always assuming that. Okay, so generous, generic, and arbitrary. So I'll start by doing an example, sort of definition by example first. So L parameters of GLN. So if we let phi be a map from WE to GLN of QL bar, and in this talk, I will always be taking QL bar coefficients. Semi-simple. Then we can write phi as a direct sum of phi I, where phi I is an L parameter for GL Ni, where the sum of Ni equals N. So then generous.
Do you want to assume phi I is irreducible?
Yes. Yes, thank you. So generous is equivalent to, for all I and j distinct, phi I does not equal phi j, and also they don't differ by cyclotomic twist. Then generic is kind of similar, but we only require that they don't differ by a cyclotomic twist. So we let them be equal to one another. And then arbitrary is self-explanatory. Okay, so now I'll give the actual definition. So a little bit of notation. I'll let Q be the coarse moduli map of par G to its coarse space, which I'll call par G spec. Then theorem is a fact, is I'm going to use the notation Q inverse of phi to denote the fiber of this map with phi. So if I take reductions, this is, the fact is that this is equal to the subvariety of the unipedant elements. Oh, I forgot a piece of notation. Let me squeeze it up here. S phi, this is going to be the centralizer in G hat of phi. So the subvariety of the unipedant elements of S phi times the Vogel variety. So, okay, I should, okay, maybe quickly define what this is. So Vogel variety are the elements in the Lie algebra fixed by inertia. Oops. Okay. All right, adjoint of phi. All right, this is a little bit messy. But so the elements fixed by adjoint action of inertia such that the adjoint action of phi of Frobenius is Q inverse N. So this is, yeah, this is aside. So this is the Vogel variety. So I want the subvariety of U cross the Vogel variety such that the adjoint action of U acting on N fixes N. And I will quotient by SV here. So sub stack, I guess. Okay, so then going back to the definitions, so generous means that Q inverse of phi should equal the classifying stack of SV, and generic means that Q inverse of phi should just consist of this unipotent part. So in other words, the Vogel variety is trivial. All right, now we're going to study how the Fargues-Schulze correspondence should look at some of these parameters. So we'll start with the generous ones. So a conjecture to Hansen is choose B pi, B in the Cotwood set of G, pi an irreducible representation of GBF such that the Fargues-Schulze parameter is generous, then C psi of IB shriek pi should be I phi star rho for some rho and irrep of SV. So this gives you sort of classical local Langlands correspondence. So you can take your B and pi and match them to phi and rho. So
Exactly the same notation as Alexander was using yesterday, right?
yes, yes. So over the generous parameters, we should have sort of nice correspondence of skyscrapers like this, and this is actually known for GLN by work of Conrad and Zoe. Okay, so then the natural next question is to understand what should happen at generic parameters. So that will be kind of the main focus of my talk. So I'm going to kind of black box sort of the main construction here. But the general upshot, I might need to define. Oh, no, okay. So the upshot is one can construct one can explicitly construct sheaves on USV mod SV for each. There are a bunch of different sheaves that show up. I won't talk about all of them, but just one of them is called nabla rho, another is delta rho for rho in irrep of SV, such that the following is true. So given some assumptions, which I'll come back to in a minute. So given some assumptions, the following is true. So we have the Fargues-Schulze map acting, so let B pi be as above, but this time we only are going to require that the Fargues-Schulze parameter of pi is generic. So then in this case, we have this is going to be given by, okay, I realized I forgot to define this a little bit earlier. So this iota phi is just, it's just the inclusion. Into par G. I don't think this has been discussed yet, but there are these other operations. So there's this IB lower sharp functor, which I'm guessing someone will mention at some point. And then some more things. So what does this give us? So one thing that this gives us is a t-exactness result. So if we look at this, then Hansen constructed something called the Hadel t-structure using these IB lower sharp and IB lower shriek sheaves. And then on, we're going to specialize to our parameter phi here. And then on the other side, we have what can be called, so sort of building off work of Bezer-Kavnikov. We have something called the perverse coherent t-structure. And then this C phi is t-exact with respect to the Hadel on the left and perverse coherent on the right. And then another application I'll mention is if we look at the Hecke operators, we can actually show sort of also building off of some work of Hansen when phi is the trivial parameter. We can show that TV is perverse t-exact. Yeah, I want to localize at the generic locus, I guess. And then, yeah, I also need to, just talking with David this afternoon, I need to restrict these things called inversely locally acyclic sheaves. Okay, now I'm about out of time, so I should stop there. Yeah, I'll stop there.
Hi, can you hear me? Yeah. So today I will talk about Higgs bundles on the Fargues-Fontaine curve. So let me first review the classical definition of Higgs bundles for a smooth projective curve over a field. So suppose X is a smooth projective curve and G is a connected reductive group, then a Higgs bundle is a pair E phi like this, such that E is a G bundle on X and phi is a global section of the adjoint bundle tensor with the Kähler differential. But this adjoint bundle, if you think of a G bundle as a excess tensor functor from representation of G to vector bundle, then this adjoint bundle is what you get by evaluating at the adjoint representation, which is the Lie algebra acted on by G. And if you instead interpret G bundle as shifts on the curve X, then it's given by E times the Lie algebra G, and you quotient by G, the diagonal action. So for instance, for G equals GLN, there's a more concrete description. You can regard E as a vector bundle of rank n on X, and then this global section of the twist of the algebraic bundle is the same as a map phi from phi to phi tensor the Kähler differential, which is OX linear.
Are you writing now? Because I'm not sure. Oh, no. Oh, you are. But it's hard to see in this color.
Yeah, sorry.
Well, yeah. Perhaps you could use a different color.
Yeah, sorry. So classically, there's some reason that people care about hex bundles. The first reason is to generalize the abelian-Hodge theory. So they use hex bundles to get something called non-abelian Hodge theory. And the second reason is that using hex bundles, you can get a variance of the geometric Langlands correspondence, which very roughly says that the derived category of quasi-coherent shifts on the moduli stack of hex bundles is equivalent to the derived category of quasi-coherent shifts on the moduli stack of hex bundles, but it's now on the dual group of G. Yeah, but this is only a rough statement. I think people still don't know whether you should use quasi-coherent shifts or maybe inco-nil or some variants of those. And the third reason is that hex bundles are used in the proof of the fundamental lemma. So now let E be a non-Archimedean local field, and with residue field FQ, and let G be a split connected relative group over E. I also assume that the characteristic of E doesn't define the order of the wild group of G. And I let XS be the Fargues-Fontaine curve. So the question is, how do we define hex bundles on the Fargues-Fontaine curve? One difficulty is that you don't really have the Kähler differential because there's no map from XS to S, and so I think there are several possible ways to define hex bundles on the Fargues-Fontaine curve. The first thing is by something called Piatek-Simpson correspondence. Hex bundles, if your field is, let's say, CP, and your variety, you have a rigid analytic variety over CP, then hex bundles on the curve is the same. The category of hex bundles on the curve is equivalent to the category of Poitou vector bundle on the curve. So maybe you can simply define hex bundles on the Fargues-Fontaine curve as a Poitou G bundles on it. And the second way, I think maybe you can use some analytic stack techniques to define hex bundles on the Fargues-Fontaine curve. And there's a third way, which is to use Engel's definition. So in his proof of the fundamental lemma, the version of hex bundles he used is he replaced the Kähler differential by an arbitrary lie bundle on X. And this is the most concrete one, and this is the one that I will use in this talk. So let me fix L a lie bundle on X. XC, where now C is a complete algebraically closed perfectoid field. Over FQ. Then I define hex bundles as, maybe I will just copy it. I define it to be a pair E phi, where it is now a G bundle on XS, and phi is a global section of the adjoint bundle tensor with L. I do not claim that it's the most natural definition, but it's one possible definition. And now let's hex G. Be the V stack that sends S to hex bundles on XS. Then you can show that it's actually an Artin V stack. And one important feature is that there's a map like this, where this AG is this is a Banach-Clommes space, and this map it essentially sends a pair E phi to the characteristic polynomial of phi. To be more precise, actually, the data of E phi is equivalent to the data of a map of stacks from XS to the quotient stack. And what this map does is that it sends this map it composes this map with the map from the quotients to the GIT quotients. And there are several, something I find interesting is that you have some abelian, by the way, this is called Hitchin fibration. Something I find interesting is that you have some abelianization theorem in this context. Actually, it also is also valid in the classical context. If you have suitable, let's say G is GLN, then for suitable A, you can classify the fiber of this map. The theorem is that if you fix an element A in AGS, where AG is this, so if you fix an element in this target, then the fiber of this map can be described as the line bundle on this CAS, which I call spectral curve. It's a curve in the same sense that the Fargues-Fontaine curve is a curve, which means it's actually not a curve. Yeah, but what's interesting about this theorem is that GLN is non-abelian, but you can relate this with line bundles on CAS, and line bundle is just GM bundle and is abelian. And so you get that hex A is equivalent to hex CA, where hex A is the stack that classifies this, so it's the fiber of this map, and hex CA is just classify this, and so hex CA is a Picard stack. Maybe I just state one more theorem. So now G is a general split connector reductive group, and hex G, the regular part of hex G is isomorphic to P, where this hex G regular is certain substack of hex G, and it classifies those maps from like this. So if you remember what I said, hex G regular, an element here, element in hex G is the same as a map from XS to GL over G. And for it to be regular, you are required to land in this particular thing. And this P classify JL bundle. Where the interesting thing is that JL is now a commutative group scheme. So again, you have relate something possibly non-abelian, like this hex G, with something more abelian. So presumably it's more manageable. Yeah, and there's actually also an abelianization theorem for a local analog of hex G, which is called affine Springer fiber. Yeah, I think that's all I want to say. Thank you.